What is power? So the definition you probably have are familiar from your high school and your freshman physics classes is amount of work done per unit time, right? So and then this is basically the definition of power you're familiar with. So in our context in this course, we are usually talking about electrical energy and electrical power. So in our context, the definition, the specific definition we are interested in is amount of work done by the electric current per unit time. Okay, so this is, as far as we are concerned, the power is defined as the work done by electric current. Okay, so let's take a simple, more very like a very generic condition. Let's just there is any generic component here. Let's say it could be a resistor, a voltage source, current sources, capacitor, inductor, whatever. Right? We don't care what which component we're considering. All we know is there's a voltage drop from left to right, from A to B, and the voltage drop is V of t, and the current going from A to B is I of t. Okay, so we want to look given this condition, we want to see, okay, what is the power or what is the rate of work being done by the electric current, right? So we know electric current is the rate of flow of charge, right? That means if there is a dq of t, charge flowing from A to B in time dt, then the instantaneous current is the dq by dt. Okay, so now let's talk, given this situation, what is the rate of work being done by the charge, right? So let's consider, when we talked about the definition of the voltage, we said, okay, in this situation, V of t will be the work you need to move a unit charge from B to A, right? That means if a charge moves from A to B, then it releases or it does V of t amount of work. Okay, so that's a unit charge. So if there is a charge of dq of t moving from A to B, then the work it does will be V of t times dq of t. So that's how much the work dq of t will do if it moves from A to B. Okay, then we just said that the instantaneous power or the rate of work will be, you should divide by the total time you're observing them, right? So then the power would be the rate of work being done, and this was the work being done. You divide by dt, and then you get V of t times I of t, because dq by dt is I of t. Okay, so then what we just saw is the power is given as the voltage times current. Okay, and this is probably also familiar from your physics classes about this definition of power here. Okay, and we just saw how we can derive it very easily. So in this course, we're going to follow a certain notation. Let's say given any device, right? And since I'm showing this as a block, just a single black box, that means this could be anything inside. All we know is a voltage drop from left to right is V of t, and the current is going in the direction. Okay, so in the direction of the voltage drop. If that is the case, then power associated with that component is V of t times I of t. Okay, so power associated is the term we use to denote the amount of work done by the current. Okay, note that this particular value itself could be positive or negative. That is why we are saying power associated. So if this value turns out to be positive, then it will turn out that the electric current is actually doing the work. But if this value turns out to be negative, that means work is being done on the current. Okay, so that's why we are using this word power associated, right? And it is important to note the direction. If I of t is in the direction of the voltage drop, okay, then the power associated is V of t times I of t. Now, for example, let's take the opposite case, where in this case I of t is not in the direction of the voltage drop, but is it in the opposite direction of the voltage drop, right? Is in the direction of voltage increase. In this case, then the power associated will be negative. Okay, So because if I of t is going in this direction, then the current in the direction of the voltage drop is negative I of t. Okay, and then the power associated is V of t times the current in the direction of the voltage drop, and that would be negative I of t. Okay, so this is just this is the notation you have to remember, and in the textbook they call this the passive convention, passive sign convention. Okay, so now let's talk about energy. Now we just said power is the rate of work being done, right? That means then if you want to look at the total energy being delivered from time t1 to t2, then you should integrate the power during that time, right? Again, you get this formula from the fundamental theorem of calculus. Okay, and here I'm representing in terms of work, or you can also say energy. The net energy done delivered from t1 to t2 is the integral of the power being delivered. Okay, so now let's talk about units. Units for power, we said power is voltage times current, right? That means volts times amperes. And we can also, so I'm just going to show you like different ways of writing the same units. So units for power is watts, first of all, and then watts can be expressed in several different ways. So in the most, if you just take this formula, it will be volt amperes. Okay, let's see, and you can replace ampere with coulombs, so it will be volt coulomb per second. Now let's go back to, if you look at the definition of volts is amount of work needed per unit charge, right? So that is joules per coulomb. And if you multiply that with coulomb per second, you get joules per second, right? Then this is going back to the definition from kinematics, which is the work done per unit time, right? So you want to notice that the relationship between these two. Volt ampere is the same as joules per second, right? And for our course, this particular way of looking at watts, it makes a lot more sense for us than this particular definition. All right, then let's look at energy again. We know usually energy in mechanical context, we measure energy in terms of joules, but in electrical context we want to look at it for watt second, right? Because it's the integral of power, integral over time, so watt second. This makes a lot more sense to us in the context of circuits than joules. Okay, let's see. Now also, let's say from a utility perspective, electrical energy, it's usually not measured in watt seconds, because watt seconds, if we don't measure time for most practical purposes, we don't measure time in terms of seconds, right? Because seconds does not usually make, is very intuitive to us. So we measure time in terms of minutes or hours and so on. So when you look at from a utility perspective, electrical energy is therefore measured in kilowatt hours, right? So what does that mean? Kilowatt hour means 1 kilowatt hour means amount of energy consumed by an appliance with a power consumption of 1 kilowatt running per 1 hour, right? So if there is let's say for example, if there's a microwave oven which has 1 kilowatt of power, and you run that for 1 hour, then the amount of energy it will consume will be 1 kilowatt hour, right? And usually, maybe you will run microwave for an hour over a year, maybe, right? So over a year, you can think of microwave using 1 kilowatt hour. 1 kilowatt hour. Again, the use of microwave may vary depending on what you're using it for, but that's not the point here. The point is, what does a kilowatt hour mean, right? So if you look at I would encourage you guys to do this. If you have access to your electricity bill, open the bill app, and if you look, they will first of all say, okay, this is, maybe per month you use 235 kilowatt hours, and they'll say, okay, we are charging you so many cents per kilowatt hour, and therefore your bill is so much. And that's how they will calculate your bill, right? So if you look at your electricity bill, they will give your consumption in terms of kilowatt hours, right? And therefore, because we measure things in hours or minutes, this makes a lot more sense to us. Okay, right, so let's stop here.